Okay, now there are some other factors that you need to be aware of in regard to equilibrium and whether they're going to have an effect or not. So one is the common ion effect that you're hopefully already familiar with by now, and that is, for instance, if we had a solution of silver chloride and we're trying to dissolve it, if there are already chloride ions in there, if there are already silver ions in there, for instance from a solution of silver nitrate, or from a solution of sodium chloride, or from a solution of hydrochloric acid, they would have chloride ions already in there, this would have silver ions already in there, and that would reduce the solubility. Okay, so when we looked at the equation, and this is the one we regard in terms of talking about equilibrium, we would talk about how, because this ion is already present here, the equilibrium would favour the reverse reaction or go to the left, and it would cause a reduction in the solubility. Okay, that's a common ion effect. But what if it's not so obvious? Okay, we're trying to dissolve this in here. There's other things that can happen. Okay, now what if there's some ammonia in there? Now ammonia is something that can form a complex. It can do that with silver, and it can also do it with copper, and then the ammonia, even though it isn't a common ion, this is not an example of the common ion effect, so I'll just write this equation back in. The ammonia can form a complex with silver, so the ammonia will react with it. Now it coordinates, and coordinates is just a fancy name for how many, we're going to surround this. It's going to be two ammonias. You do the square brackets. Now the charge is going to be plus, and it's going to be 2, so make sure it's balanced, this equation. So you should be able to write that equation. Things to take care of. How do you work out the charge? Well, there's no charge in ammonia, so if we add ammonias around the silver, it's still going to have the plus charge on there. Okay, you do the square brackets and just take care to put 2 there, because you've got 2 here. Okay, so it coordinates 2. So because in this case with silver, these silver ions here are being removed and forming this complex up here, that means the equilibrium will shift to the right and favour the forward direction, meaning more of it will be able to dissolve, and that increases the solubility. So you talk about all those things, about the complex, about the equilibrium shifting to the right, and also about the increase in solubility as a result of the complex with ammonia. Okay, now it can also form complexes, ammonia can form complexes with other things, and the reality is in NCA you're going to only be asked for questions and examples where it's going to happen in terms of ammonia reacting with something, so or forming a complex I should say. So if it was copper, it could form a complex. Now most of the time the coordination number is always going to be 4. It's only silver in the case that you expect to know that it could be a different number, which is 2. So it's always 4 except for silver, which is 2. So this would be a similar thing if you say copper hydroxide in solution. And so on the other side we'd have copper 2 plus and 2H minus, right? So because the copper ions once again are forming this complex with ammonia, that means we're going to get equilibrium shifting to the right, and more will be able to dissolve, and that increases the solubility. Okay. Now there is one other complex you're expected to know, or there's a few examples of that, and that would be hydroxide, and that can form a complex with Al3 plus, zinc and lead, and they all coordinate 4. So for instance, if you had aluminium hydroxide, Al3 plus and 3OH minus, so we've dissolved aluminium hydroxide. Now, initially what would happen if you added more hydroxide ions to it? Now, that would be an example of the common ion effect. So you would have, if you had more hydroxide ions already present, the equilibrium would shift to the left and less would dissolve. There's something interesting that happens here. If you keep on adding hydroxide, you'll get to a situation where it will form a complex. And you'll have seen this in Year 12 chemistry, where you get it's reacting with another hydroxide ion and it forms this complex. Now the charge in this case is just going to be a minus, okay? Because it's 3 plus and 4 negatives leaves over a charge of minus, and these complexes should be AQ. You could equally write that equation like this: Al OH 4 minus. Okay. Now that once again is going to increase the solubility. So because you're removing the you're removing aluminium hydroxide ions, that means now you're going to have the equilibrium shifting to the right, so more of this, in fact almost all of that, will actually end up dissolving. So in this case the complex initially, if you add just a little bit more hydroxide, will force the equilibrium to the left, but if you keep on adding it, you'll form this complex, and once this complex forms, the equilibrium will shift right over to the right and it'll redissolve. Okay. Now with zinc and lead, the equation is just still very similar. I'll just do it with 4 hydroxides. You get zinc OH4 and 2 minus, because you've got 2 plus and 4 negatives, and that leaves 2 negatives there. Okay, make sure you include the 4 because there's 4 here as well, right? So all of these complexes here, aluminium, zinc and lead, will complex with 4 hydroxides. Okay, so this is a case of where this complex removes zinc ions, hydroxide ions from solution and allows a lot more to dissolve. Okay, so that's the second possibility. You can, obviously there's a common ion, the complex, and then there's finally reactions. Okay, what if you were trying to dissolve calcium hydroxide in a solution that had pH of 2, or it had 0.1 mole of HCl, or there's sulfuric acid present? In all these cases we're basically saying that it's an acidic solution, there's H3O+. Now naturally that can react with hydroxide, so that's the third possibility, and usually we're talking about acid reactions. Okay, so if that reacts with the hydroxide, the equilibrium will shift to the right, and that will mean more calcium hydroxide can dissolve, so they'll increase the solubility. So this is one further thought you have to consider. In solutions, is the ion the same? Possibility of a common ion. Is there ammonia hydroxide involved in the equation? Because if there is, you've got to consider the possibility of, or in a situation that a complex may form. And finally, can it react? Okay, those are the other factors that you have to be aware of. And normally you have to be able to explain them using equilibrium principles, how the equilibrium will shift to one side once, for instance in this case, the hydroxide has been removed by reacting with the hydronium ions, and it shifts over to the right, allowing more solubility. Okay.